Welcome to this episode of the Verilog Bench. Today we're going to be looking at the AMBA Core Specification from the software and firmware point of view. This is the software and firmware view of IHI0011A. The document is not a driver manual. It is a bus architecture specification. So the useful mental model for software is not raw waveform control. It is the path from CPU to system bus, to bridge, to peripheral, and the platform behavior that appears at that boundary. From software, the AMBA2 hierarchy looks like a memory map with different kinds of targets behind it. The CPU is one requester, but DMA and other masters can share the system bus as well. Many low-bandwidth peripherals live behind an APB bridge, which is why some regions behave like simple register banks instead of memory system fast paths. The biggest software-relevant point in this document is why APB exists. It is meant for program control peripherals with simple register maps, not for high-bandwidth data flow. That design choice is why many timers, UARTs, and similar blocks feel straightforward to program, even when the system bus behind them is more complex. When software accesses an APB peripheral, the hardware side is doing a setup cycle followed by an enable cycle. There is no burst model in APB here. Address and control stay stable across the enable phase. That is why the peripheral edge usually feels simple and ordered compared with the more flexible behavior on the system bus. APB simplicity does not mean zero latency variation. The bridge hides peripheral protocol detail, but it does not erase AHB or ASB contention before the access reaches the peripheral side. So software may see some regions as slower or more variable than others, and that could be a platform fabric property rather than a register block fault. Software teams also need to remember that the CPU is not the only active master in the system. DMA can compete for bandwidth, change latency, and expose corner cases around shared memory or shared peripheral paths. In bring up, these issues often present as timing-sensitive behavior rather than as clean, repeatable logic faults. Alignment and Endianness are software-relevant even though the details are defined in hardware terms. The bus requires aligned transfers for their size, and byte lane interpretation depends on the system Endianness. The document is explicit that all modules and bridges must agree on that Endianness, so software should not treat it as a dynamic per transaction choice. When an access fails, software often sees only the platform symptom. Underneath that, the cause might be decoder policy, a protected region, or a slave-side error rule. The bus architecture matters because it defines where those policies can live, even if software never sees the raw response encoding directly. One useful edge case note in the document is the section on interfacing revision D APB peripherals to revision 2.0 APB. This is not the normal case, but it matters in legacy SOCs where old peripheral IP is reused under a newer bridge assumption. If bring up seems odd only on older blocks, this kind of interface mismatch is worth checking. The safe software model is straightforward. Treat simple peripherals behind APB as MMIO targets. Expect some latency variation because of bridges and share masters, and respect the platform's alignment and Endianness contract. Do not try to reason about cycle-level bus timing unless the platform documentation explicitly makes that visible. The software takeaway is that AMBA2 matters as platform context. It explains why some regions are simple and predictable, why others show shared bus timing effects, and why bridges are part of the debugging story. That is the level of understanding software teams usually need from this document. If this software view was useful, like and subscribe to be notified of future videos. Next, we leave the Core Rev 2.0 document and move to the multi-layer AHB technical overview, which is an architecture and topology topic rather than new protocol. To close, here is a glossary for the main bus family acronyms. AMBA stands for Advanced Microcontroller Bus Architecture. AHB is Advanced High Performance Bus. ASB is Advanced System Bus. And APB is Advanced Peripheral Bus. MMIO means Memory Mapped Input-Output. DMA means direct memory access. CPU means central processing unit. SoC means system on chip, the complete integrated platform using these buses and peripherals.